Good morning, everybody. Thank you for joining us. It's interesting, and you could probably tell very quickly that the team is really quite enthusiastic about connections. So one of the things that, the way I think about that is you've probably heard the phrase, the smartest person in the room is the room. All of us collectively are so much smarter than any one of us, or probably any subgraph of us on our own. So definitely take the opportunity to meet and soak up some of the smarts in the room. So my name's Amy Hodler. We are going to talk about graphs and AI and how they enhance. And it was an interesting data point that Emma brought up about the trends, the popular trends being all about AI, machine learning, and graphs. And those two things go together naturally, hopefully you can see. But I want to start off with why I got interested in this, because I feel like it's just a fun story to share, or meant a lot to me. Is I actually got interested first in network science. And we know networks, mathematical representations, use graphs. But this cartoon, I really enjoy. It's from, unfortunately at the time, it was right before the 2008 crisis, the economic crisis. But it was all about financial contagion and how things spread through a network. And our views of how things spread and contagion in financial situations had a very global look at this point in time. We did a lot of research. There was a lot of network science that came about the density of the banking system and different trading systems. And I like that this kind of shows that things spread, but they also amplify. So I started to really look at this a little closer. But we probably have felt lately that we're a little more local than what we used to be, that things happen faster, that the connections are surprisingly both small and complicated. So I don't know if any of you saw the news this weekend or checked your 401k this week. I actually haven't yet because I'm not quite ready for it. But something as small as a single tweet changed our markets and had an impact. And I would have never have thought that something like that was even possible. So if you think about our economic systems and the networks that they are a part of, and the ripples, that things that you would have thought could never be connected, things have become much more local. And what's interesting is over the last probably 10 years as well, our view of what that is also kind of come a little more local. So we used to do the network science over the big markets and how things spread and big events. And now we're seeing, single tweet, and it makes a change. So what's interesting is our customers are also going more local, also looking more local. So there's a large financial customer we work with that wants to look at investments and wants to understand contagion within their potential investments. Is this a good investment or not? And this particular example is a manufacturing of trucks, so truck manufacturing. Well, what happens when the tariff on steel goes up? What happens if this truck manufacturer can't pay component suppliers for a couple months? What's the potential spread with not just this manufacturer, but how about a shipping company that relies on them for some specialized equipment? Perhaps it's a refrigeration that maybe actually ships medical supplies. And so there's a potential for the ripple. So it's not surprising that we're working with institutions to try to look at what that contagion looks like, to look at it like a graph, because it's obviously connected, and it's connected in ways that you wouldn't think of by just looking at kind of a regular supply chain logistics. So looking at that and looking at it as a graph is one thing, and that helps considerably in understanding it. But what the next thing they want to do is they want to learn their paths. They want to use machine learning to say, we know these things kind of travel this way. Can we develop a meta path? Can we learn on that path? And then can we make more stable investments? And so this is an investment scenario, but ultimately we're talking about how do we make our financial systems more robust, less fragile. So these are the kind of things that got me interested in graphs and in machine learning, is kind of understanding this better. And if you think about, financially in the systems, you can imagine how connected these are. But anywhere that there's lots of data and lots of connections, and actually so many that it's hard to unfold them, those are the areas that we see graph analytics and graph data science being very applicable. And a lot of these, you'll notice, are similar to the things that Emil talked about. Not surprising, because we're talking about connections. Financial crimes is a prominent one that we work with a lot of people on. That can be anything from looking for fraud, but also anti-money laundering. What kind of a group behavior does this group have? Is it anomalous? This might indicate that, that something nefarious is going on. Drug discovery. So this is an exciting area. If you think about it, drugs target genes, they target symptoms, they target profiles of particular individuals. They have symptoms. There's good outcomes, bad outcomes. These are all very graphy things. And if we can help people discover that, learn what some of those linkages might be, we might help them repurpose drugs for new uses, or potentially target and have more personalized medicine. Recommendations, another area where there's a lot of graph and machine learning going on. In particular, if you think about a recommendation and just looking at somebody similar to somebody else and recommending a product, that's one way to do it. But using graphs in machine learning, you might be able to look at the path that somebody takes to buying a product. And if I know what the path is that they take, then I can develop a pattern on that path, then I can learn on that path, and then when somebody else is halfway through that path, I already know where they're going, or I can recommend where they may want to go. Customer segmentation is another. So we think about all the investments that we make in marketing and targeting to groups of individuals. How do we make sure that we understand what communities they belong to, what interactions they have with other people? That's going to help us target better and do both better for the end customer as well as businesses. Cybersecurity, very similar to financial crimes in a lot of the analogies. If you're trying to do something like intrusion alert, you're also going to want to know, is this a pattern I've seen before? Is this not a pattern? Maybe that's a problem because it's not a regular problem or not regular pattern. Churn prediction is really interesting. So things that you might want to predict there, how is somebody, or is somebody about to churn? That's kind of an interesting problem. The other thing is, how about after they churn? Are they influential in their network? Maybe I have a subscription service, and when mom goes to another subscription service, by the way, half the family goes with her. So you want to be able to predict these rippling effects. Predictive maintenance kind of goes along the same line. You want to predict these rippling effects. Interesting concept here, or example here, is something like tires and tire wear. So how long should you have your tires on? When do you want to have scheduled maintenance for maybe your trucking fleet? Well, it depends on the tire, depends on the weight of the vehicle, depends on how old the vehicle is. How about understanding the age of the person driving or where they drive, because roads are different in different locations. So all these things, all these contextual items that Emil talked about go into understanding the item and then understanding how you can predict possible maintenance requirements. Emil talked a lot about search and MDM and master data, and that just always reminds me of, hey, where did a lot of this popularity in graphs start? With Google. And think about PageRank. PageRank is probably the most well-known graph, it is the most well-known graph algorithm out there, all about originally providing a credible page to users and serving people looking for things. So we're not the only ones thinking about this. Emil talked about a few items. This is the paper that came out, I think it was last October. It kind of rocked the AI graph world, if you will. Very influential. This is ZDNet kind of coverage of that paper and trying to summarize it. But basically, we had people from Google DeepMinds, MIT, and other really smart people looking at where are we with machine learning today, and how can we do better? Where do we need to do better? And what potentially may help us get to that next step in machine learning? And what's interesting, of course, I love to hear, is the realization that graph networks are bigger and a bigger idea than any one type of machine learning approach. And that's a big statement. And the reason why they made that statement is just right below there, is the ability of graphs to abstract and generalize structure. And anybody who's gone to a whiteboard and done that understands that you just can abstract so much and generalize that structure, and that's something that other neural nets just can't do. What's kind of funny is the other thing that they brought up was they said that other problem is mathematically not intractable. You know, we'll overcome that, but we're not really sure where all the graphs are going to come from that we're going to run these graph networks over. And as a company that's been in this space for a long time and working on these, we believe that that will be something that we can help with. And so for us, it's kind of an exciting marriage between some really great ideas and some gaps that we can help with. So that's kind of that's a research. It's an exciting area. It's an area we believe that the market's going to go into. But one thing that we hear a lot from customers is, oh, I'm really excited, now what? How do I start building my graph machine learning and data science model? And there are a few things to think about, and these are just like big buckets. You want to have, you know, your data sources. You need your native graph platform if you're building a graph machine learning model, and you need to have some kind of machine learning. So you have this kind of workflow, and I'm going to show you an example of what this might look like with Spark, and that is because so many of you have Spark out there or have data flowing through Spark, and quite a bit of it. So just recently, you may have heard that there's a new project in Spark coming out. It's slated to come out this fall called Spark Graph. We've been working with Databricks for a while on this. And what that will do is it will bring Cypher to Spark so that you can do your label property graph, your property graph types queries. You can explore your data as a graph in Spark. It's not persistent, which means that if you do want to persist it, you can explore it, you can do transformations. About the same time, we'll have Morpheus ready as well. That's an open source project that is actually available today, but we'll be doing more with Morpheus to allow people to do further transformations and then integrate it with Neo4j. So this allows you to take your massively scaled data sources, explore them, see if you have graphs that you think you might like to build an application on, bring it over to Neo4j, do your native graph processing algorithms, and persist it, and then also do machine learning as well. So the idea here is if you do have Spark, and I know many do, use it. It's great. It's very scalable for lots of data. It has a lot of pipelines, has a very powerful machine learning library, but because it's not native and because it doesn't persist, when you do decide that you need to do more serious graph analytics, when you decide that you have a graph of a size you want to now build an application on, that you can bring it over to Neo4j, build your graph solution, persist your graph, and use dynamic graphs as well, so you can make changes in your graph. As I mentioned, we've got the native query and graph algorithms. What that allows us to do is, because we operate the algorithms in memory and do the analytics in memory, it's the performance is quite significant. It's all in a single memory space so that you can operate over your entire graph. And that's important from a graph algorithm standpoint, because a lot of graph algorithms aren't amenable to parallelization or aren't amenable to chopping up the graph and chasing analysis over different areas of the graph. They want to consider the whole graph. It's very global in the way they look at things. And then, of course, we're all about graphs. So we have quite a few graph algorithms. I'll show you just a list later. And we are always continually adding to those. So that's cool. So how do you actually do something? How do we actually get started? So Emil talked about these three major milestones, I would call them. These three major phases. We've got things that we've been doing for a long time and very mature, things we're working a lot on now, and then things that we're moving toward in the future. But these are actually, there's actually more steps than this. It actually kind of folds out. And so I wanted to walk you through examples in each one of these steps of how you might get started. The x-axis on the bottom is enterprise delivery. And that's kind of a sense of how long is it going to take these technologies to be ready for an enterprise to adopt. And then the y-axis is data science complexity. It's just how hard is the math, how difficult of a problem is. And so something like knowledge graphs, they've been out for a while. They're very mature. It's solid. People know how to use them. People are implementing that. It's just a great starting point if you're not already there. Feature engineering, especially query-based feature engineering, you're starting to build some machine learning. You want to add some graphy features to your machine learning, but you still need a subject matter expert. Graph algorithms for feature engineering means unsupervised, so we can throw graph algorithms at our data, do some analysis, grab even more graphy features, and put it into our machine learning model. Graph embeddings are really interesting if we want to talk about learned representations of our graph. It's kind of a halfway between algorithm and feature engineering, and it's just starting to get into deep learning. It's a required step, and it's just kind of inching us towards that. And then graph neural networks, as Emil talked about, is keeping both the output and the input in a graph and doing native learning. So an example in query-based knowledge graphs, this is, as I said, it's very mature, it's been out there, but people are still doing some really inventive things here, which I find kind of exciting when people do cool things out of very well-known, solid technology. So this example is actually the graphic is a screenshot of a dashboard that our solutions team is working on. I don't know if any of them are here today, but I hope they are. And it's a dashboard based on multiple knowledge graphs that Refinitiv uses. And Refinitiv is a spinoff from Thomson Reuters. It's multiple graph layers of financial information. It includes things like regular corporate data that anybody might be able to access, but also streams in external news to keep that information up. So let's say there was a news story and a financial market changed, or a news story and somebody's stock went on. How do you correlate that? And so they allow people to go in and search. The dashboard makes it easier for them to interact with the data. They can also do customized weightings, so you can weight what kind of relationships maybe are more important for your portfolio. And then there's a couple different tools with different dashboards, credit risk, investment risk, and news recommendations. So it's well known, but people are adding on applications now to knowledge graphs, which is very fun to see happen. Okay, next step would be using query-based feature engineering. And this is where you still need a subject matter expert. They know what's predictive in their network. They just can't get to it. It's just too hard. If it was in front of them and you gave them the answer, they could say, well, yeah, that's predictive, that's not. But pulling that out of big data sets can be very, very troublesome. So this example is from het.io. They use Neo4j as a backend. They have a Neo4j knowledge graph. They're using over 40 years of biomedical information. And oh my God, is that a lot of information. So things from genes, disease, what the compounds is in treatments, what are the side effects, what are the outcomes, what are the pathways things have taken. So very graphy problem. Before I forget, you can go to het.io. They expose their data, and they expose the Neo4j browser. So those of you that are already familiar with Cypher, you just go to the website, play around. It's kind of fun to do some queries and look at the data, and maybe you'll discover something new. But what they are trying to do is actually, or one of the things they are trying to do, is actually try to say, are there links between genes and diseases that we can predict? Like, there are links there. We just don't know that yet in our data. And so what they're trying to do is look at the topology of the network and understand where there's links and relationships that we just haven't seen yet. And the way they do this is kind of interesting. So if in this example, you can see we've got a gene, IFR1, we've got a disease, multiple sclerosis. Yeah, that is visible, great. That there's not a direct link, but they can look at all the paths, all the secondary and tertiary paths between IRF1 and multiple sclerosis. So they look at that, They do some analysis, they do some weighting. Remember, we need SMEs in this still. This is query-based. And then they develop some features. So they develop some features that they do some machine learning on. And then they end up with probabilities. So they have a probability that IFR1, in this case, is linked to multiple sclerosis. So this is an interesting way to infer relationships that we haven't even seen yet. And in this case, if you can do that, then you know that any drug that is targeted towards IFR1 is potentially a really good target for multiple sclerosis. Now, what that means is that if the drug is already out on the market, it's already gone through trials, we can repurpose it for another use and get a new treatment to people faster. So really important work there. And if you're interested in getting started with knowledge graphs, you're going to see some similarities here with how to get started. You can use Spark Graph to merge your distributed data, reshape it, transform it into a graph, go from tables to graph, and then kind of use Cypher to explore it. Does this look graphy? I can run some graph algorithms in Spark Graph, take a look at what's in graph frames to kind of understand what's moving over into Spark Graph for algorithms. But I can explore that, take a look at it, and then once I've decided that I want to use that, I can now bring that part of my knowledge graph over to Neo4j to persist it, because if you're building a knowledge graph, you probably want to persist it. And then have your experts build additional features that you can then use in your machine learning pipeline. And just to say your machine learning pipeline, as most of you probably know, there's a lot of different tools you may use. If you're a big Spark shop, you're probably using Spark MLlib, but probably also Python, R, and other tools as well. So let's look at feature engineering using graph algorithms. This is probably where we spend the most of our time right now, because a lot of customers have kind of taken those initial steps and they're now ready to take the next step. And we can think about feature engineering, developing those graph-connected features, is really how we develop new, more meaningful information, more predictive information that we didn't have. It's kind of, I want to say, it's almost like getting something for free. You already have this data. Use it. We can actually generate more information out of what you already have that you can do machine learning. And some of the things that you might want to do is look at, how are things clustered? What are the relationships? What are the communities? Once you're starting to look at that, you would extract that to a form that a machine learning model could handle. And that would be going to something like the table that is listed below. Basically, you have identifiers and scores. And then you take your scores, you do your learning, and you might want to predict something. I don't know if you can tell here, but there's actually a Game of Thrones visual here. Can you guys actually see that? Anyhow, so Tyrion, this must be an early series, has a high page rank. But you can see we've actually predicted that Joffrey is not alive in this example. So, it's kind of fun. And okay, side note, if you have fun with this stuff, we do have some Game of Thrones data sets on our sandbox you can play with. So that's kind of how you might extract and engineer features. There are a lot of algorithms you could use. We have up here the ones that we see most often used commercially, but there are a lot out there, a lot in the academic world as well. Community detection helps you, as you would imagine, find communities, but also looks at how tightly things are clustered, and if you need to partition, optimal areas to partition. Centrality is all about influence, PageRank being the most famous centrality graph algorithm, but it also looks at other types of influence as well, like how fast a node can reach other nodes. Pathfinding is probably, I kind of thought of as the foundational graph algorithm category, and that's all about optimal routes. Link prediction is a heuristic to estimate how likely things are to connect in the future. I have an example of this in the afternoon, I think 3:15 or so, that will walk through a workflow using this. But that looks at the topology and says how close are these two items. Similarity, how similar are two items? Pretty simple measure, can be very predictive. Graph embeddings, kind of learning representations or about connectivity or the overall topology of a graph. So an example of connected feature engineering in financial crimes would be detecting fraud, and we'll talk a little bit about that. Most companies, especially if you're a larger company, have some model or heuristic or pipeline to identify fraud already, which is fantastic. It's a big problem, but it's also very complicated. When you think about the economic model I talked about earlier, there's so much information people have about us in financial institutions. What location do I live at? Who lives in that same location? Where do I work? My demographic? How often do I go to the ATM? There's all this information that we have, and it's very difficult to figure out, okay, 4 hops out, how many fraudsters? You would think 4 wouldn't be too many, but we actually hear 4 is very difficult for people. But also beyond that, graphs can help with accuracy and precision by adding in features like connected components. So connected components just looks at, very simply, how many people in this little area can connect to each other through other people. So it's kind of like a little island. And if that island is disjointed from your entire graph and there's a lot of activity going on, there's potential fraud there, especially first-person fraud. PageRank, generally about influence, but it's also been used to look at transaction volume because PageRank looks at direction of relationships. So we can do PageRank and look at the directions of relationships and see what seems anomalous, what's of a high influence, if you will. Louvain modularity is one of the many graph community detection algorithms. That one's kind of interesting because it also allows you to dial up and dial down how tight you want to look at a community. So maybe you don't want to have too many false positives, so you want to dial it down a little, let some minor issues go through and focus on the big ones. It also lets you find sub-communities, and that's really useful if you're trying to look at hierarchy in your data and hierarchy in potential fraud rings. Jacquard similarity is a simple measure of how similar 2 items are based on common attributes and properties with them. And that's something you can run very quickly. Let's say you have a profile of a fraudster, and you just want to run that really quickly through your network and say how many nodes match this profile with a 80% overlap. And just so you don't think that I'm making all of this up, I actually pulled some data looking at US patents over the last 10 years. And if we think of graph and networks, there's been over 48,000, so almost 50,000 patents around graph, fraud, and anomaly detection. Very active space for very good reason, because it's a very hard problem. So if you're interested in getting started with feature engineering, again, if you're a Spark user, and you don't have to be a Spark user, I should say. You can start with another data source, but there is a lot of information out there. But you would move to the graph to persist your graph again and run your native graph algorithms, run a lot of variety of algorithms, and then write back to your graph. I told you there was a lot of graph algorithms in Neo4j. We've got over 35. We keep adding. Every time I turn around, our labs team has added another one, which is really cool, but it's hard for me to keep up with all of them. If your eyes are good enough, you can see in black, there's a couple ones bolded here. These ones are also in Spark. They're in graph frames. You can see that there's a little difference in how many graph algorithms we have. A part of that is just our passion for the space and making tools as easy as possible and bringing them to people. But the other thing is that reality that I mentioned of having having the ability to do in-memory computation over an entire graph makes it easier for us to do certain algorithms. It also makes it easier for us to optimize those for the performance of our platform and a native graph platform. So stepping forward to kind of the next level, the next area that we see people starting to go in, this is that toe in the water of deep learning, is graph embeddings. Now, graph embeddings transform a graph into a feature vector. Emil talked about features. A feature vector is a collection of features. So you can think of features of features, if you will. But it describes the topology, connectivity, attributes of the nodes at the edge. Usually the vectors have some form of dimensionality, some kind of x, y, z coordinate as well, like how close are they to each other. There are three types of graph embeddings. There's a node or vertex embedding, and that really describes the connectivity of each node, like every single node. What's their connectivity look like? Path embeddings are describe the traversal over a graph. What are the paths over the graph? Graph embeddings themselves encode the entire graph into a single vector. And that has use cases in some areas where the graph itself has information, that has attributes that have some kind of learning capability. I understand from our data scientists that this is actually really significant in chemistry, because the graph itself actually has some predictive qualities. The graphic at the bottom is a picture from a deep walk talk paper about how they go through this approach. Now they look at the graph and then they do a random walk and a sampling over that. Then they train that model using gradient descent and compute the embeddings. So that's just one approach, and it kind of shows that there's a nice process to get from graph to your embedding. Now, a really cool example, and I think graph embeddings are going to be really important for recommendations. A cool example from eBay, they published this paper about reasoning over knowledge graphs for recommendations. Quite clever, I think. And this example is a user who happens, Alice, who happens to like a song, Shape of You, and would like to be able to recommend another song. Now, the interesting thing is the way a lot of recommendations done today use collaborative filtering. They say, well, Alice is somewhat like Mary, and Mary liked this other song that maybe she likes Shape of You as well, and she likes something else. I'm going to recommend that. So it's kind of based on the node, based on Alice. But what they're doing, what eBay's doing here, is they're actually looking at the graph around the song. So the song has a whole knowledge graph of its own. So the song has people who were, maybe people who were on the record, who produced it, who wrote it, who sang it, what genre it's from, what language it's in. You know, there's all these things around it. And we'd like to be able to estimate what path somebody might take through those items to get to another song. So on the other side, we have songs that the user may be interested in, and we'd like to understand what those paths are, and actually, which one would they be more interested in? What's the probability that they would like Castle on the Hill or I See Fire? Sorry, I don't listen to a lot of music, so I have no idea if those are popular or not. So what they did is they actually looked at an embedding layer. The blue items are the nodes, Alice, Shape of You, Ed Sheeran. The pink items are relationships. So they're looking at both nodes and relationships, and they're walking through, they walk through six hops out, but they walk through each of the potential paths. And then they use a LSTM layer to embed that, and then they do learning on it, and they come up with probabilities for paths. Now, I kind of get excited about that, because in my first, a few minutes ago, when I said, what if we could help somebody understand that they're halfway through a path that would have the probability to take them left, right, song A versus song B. So I think for recommendations, this is a really exciting area. If you're really excited about this as well, I would say go ahead and get started with your foundational elements. We can help you with that. Stay tuned. We are working on two implementations for DeepGL and DeepWalk. We're working with some early customers on that. We expect to incorporate that into our graph algorithms libraries in the next few quarters. So we're working on it. If you're super excited and you just have to have this, come find one of us later, and we can talk about early adoption and taking a look at what uses you need to use that for. The final step, I'm just wondering, I bet that's not the final step. I bet there's other steps in the future. But in the foreseeable future, where we see graph data analytics and graph data science going is that graph neural network. And to just kind of quickly summarize what that might be or what that looks like, this is just deep learning. It refers to looking at multiple layers of a neural network using this gradient descent, trying to optimize some function. Your input, I probably should change this graphic. Your input and your output aren't the same here, although they kind of look that way on this visual. But you also have these hidden middle layers. So input, output, not the same. Middle layers are hidden here. Graph native learning, and this is from the paper that I mentioned earlier. It's an excellent paper. Graph native learning refers to, as Emil said, input, takes an input as a graph, performs all this computation, and then returns it as a graph native. Now, the paper is fantastic. It took me probably half a day to get through it and try to wrap my head around it, because there's some really exciting ideas here. And after talking to a couple people, in particular data scientist Alicia Frame, to understand, okay, what's the big so what here? Why, okay, this is cool, but you know, what does this mean for me? So it allows us to do a couple different things in a couple different new ways. You know, first, input and output the same as a graph means that our visibility of how things changed in the intermediate steps, because the intermediate steps are graphs. So if I'm making a change in my predictions at each step, I can now do some validation. I have visibility into how that happens. And this kind of goes to the AI explainability that we've talked about in the past, is we don't want AI, we don't want deep learning to be a black box. If there's a decision made, we want to know how and why that decision was made. This is the first step in getting us there. This helps us understand a little bit how the learning progresses. So that in itself is really cool. It also is easier for data scientists to work with, because if you're going to go to a whiteboard and draw something and then compute on it and your output is a number, it's not quite the same as outputting as a graph and being able to compare your input and your output and kind of understand how that flows. The third thing that's really exciting, that I think is really exciting, and I'm not sure I've quite wrapped my head around, is if you think about a lot of the things we're trying to predict, we're talking about predicting single items. We're talking about predicting single paths. What's the path from this music to that music? But real world, these things are all interrelated, and there's multiple things going on at the same time. So maybe while I'm looking at this music, I also happen to buy something different. I also happen to decide to get married. I also happen to, the flower shop went out of business. There's just all these things going on at the same time. And this potentially has the ability to look at multidimensional learning together. So you're updating the graphs and you're doing predictions on multiple things. So this is really exciting. It is research, but it is somewhere that we think that the machine learning and the AI market is headed, and we think it's pretty important. There are some people actually doing this. They're in the chemistry area. So this example, and I'm not a chemist, so I hope I don't slaughter this too much, but I had a chemist explain it to me. So this is where they're actually trying to predict new molecules that may form. If I have these different components, I put them together, what's going to come out the other end. And they basically take a molecule and they remap it to a graph, because molecules are very graph. They add nodes and relationships, and then they encode that so they can do some machine learning. And what that gives them the ability to do, and you can kind of see that in the bottom area, is to not just predict. So they're adding reactants to each other and a reagent, and they're predicting a new, let's see if I can get this to work. So they're predicting a new compound here. So this in and of itself, that's exciting. But what else they're able to do is say, okay, well, what was the flow? What was the electron path that got us there? So that is one example of how you can use graph native learning. So I hope you can see by these steps that graph data analytics, graph data science is progressing forward. I'm kind of excited about this time frame in our history. There's a quote, and I don't remember who said it, that there's nothing as powerful as an idea that's time has come. And I feel like the time has come to actually bring graph and machine learning together and watch it kind of flower into this new potential. So lots of steps you can take now. We can help you with things that you're doing today, build your foundation, and then we'll help you kind of move to where we're all going next. So Resources for you, if you're on the business side of the house, we've got a website with some use cases and some information. We're coming out with an AI white paper in the next week, so that'll be there. If you're a data scientist, we've got a sandbox. I mentioned about the Game of Thrones. We have other sandboxes as well, but you don't have to load any data. We've got guides within them that you can click through. We also have developer guides, community, lots of resources for you. We just offered, or not offered, but we're offering a O'Reilly book that was just published on the 15th. You can download it for free here. I'm actually one of the co-authors of it. My colleague, Mark Needham, is the other co-author. He could not be here, so I am bringing Mini Mark to all my events. I can't promise that he'll sign, but maybe we could stamp or something like that. For those of you willing to participate with us today, we are actually offering hard copies of the book at lunch, and those will be available at that time. So with that, I really appreciate everyone's attention. We are about to head into a break, so get your coffee, get your fika, and come back and we'll keep going. Thank you. Oh, I didn't explain fika. Oh. Yeah.